In this video we'll be finding out about atoms and about substances which are made from only one kind of atom, which we call elements. While the Greek idea of earth, air, fire and water being the four elements has not survived, the Greeks also suggested that if you took a substance and kept breaking it into smaller and smaller pieces, eventually you would have a single particle of that substance which couldn't be divided anymore. This they called an atom. The idea was correct. Everything in the world around us is made with atoms as the basic building blocks.
Copper and tin are made up of particles called atoms. In pure copper, all the atoms are the same as each other. It's the same with tin, but tin atoms are bigger. A pure element is made of just one type of atom. The idea of the atom goes back as far as the ancient Greek philosophers. Democritus was one of the first to think that everything was made of particles. As he looked at a pile of sand, he could see it was made of grains. Democritus thought that if you could look close up and actually see inside any substance, you'd find that it too was made of tiny particles. If you take a piece of cheese and cut it in half and then in half again and keep on cutting, eventually you'll be left with a tiny grain of cheese. Your knife isn't delicate enough to cut it any further. But Democritus imagined that you could keep on cutting. He decided that you would eventually get to a point beyond which it couldn't be divided anymore. Atomos is Greek for not cuttable, so Democritus called the smallest unit of matter the atom. Back then, he had no way of proving whether atoms existed, but today, high-tech machines allow us to see them. A layer of aluminium gives this CD its silvery sheen. But at greater and greater magnification, it looks quite different. Keep on magnifying the image thousands and thousands of times, and eventually you can see the individual aluminium atoms.
We need to appreciate that atoms are incredibly small. For example, look at a single one of your hairs. The width of one hair is about 500,000 atoms across. If you could expand things until you could see the individual atoms, you'd need to expand a single drop of water to be 15 miles across. In a volume of air the size of a sugar cube, there are 90 million atoms. Scientists have found that even individual atoms are themselves made of smaller particles. All the different types of atoms we see in the periodic table are made from different combinations of just three particles called protons, neutrons and electrons. An atom contains a nucleus at its centre, which consists of a cluster of protons and neutrons, and around this there is a cloud of orbiting electrons. Protons, neutrons and electrons are themselves much smaller than an atom, so most of an atom is just empty space. Atoms of the same substance always have the same number of protons. This is what makes them the substance they are. For example, an atom with 15 protons is a phosphorus atom, while an atom with 16 protons is a sulfur atom. We call the number of protons the atomic number, and we arrange atoms in order according to their atomic number in the periodic table. In an atom, there is one electron orbiting the nucleus for every proton in the nucleus. The atomic number also tells us the number of electrons in an atom, but atoms can lose or gain electrons to become particles called ions. They can never lose or gain protons. Electrons weigh hardly anything compared to protons and neutrons, so it is the protons and neutrons in the nucleus that give an atom its mass. We therefore call the total number of protons and neutrons in the nucleus the mass number. You may have realised that if the mass number is the total number of protons and neutrons, and the atomic number is the number of protons, then the difference between those two numbers is the number of neutrons. Mass number minus atomic number equals number of neutrons. You will have seen from the periodic table that every different type of atom has its own symbol, either a single capital letter or a capital letter followed by a lowercase letter. These symbols come from the name for that type of atom. For example, Be for beryllium or C for carbon, but in other cases the symbol comes from the Latin name, for example Au for the Latin aurum for gold. This means we can describe any atom using its symbol, its atomic number and its mass number. Here we can see that a beryllium atom has an atomic number of 4, so it has 4 protons, and a mass number of 9, so it has 9 protons and neutrons altogether. The difference between 4 and 9 is 5, so there must be 5 neutrons in this beryllium atom. The name for a substance made of just one type of atom is an element. These are the substances collected in the periodic table. Elements can be made from individual separate atoms, like in helium, or from 2 or more atoms joined together to make a molecule, like in the element hydrogen, which is made from pairs of hydrogen atoms joined together. There are 98 naturally occurring elements that we've discovered, with atomic numbers 1 to 98. Physicists have managed to make some heavier elements by smashing together lighter atoms, and these have atomic numbers greater than 98. All the known elements are collected together in the periodic table in order of atomic number. The periodic table isn't just a long list though, because it also collects together families of elements with similar properties. The rows in the periodic table are called periods. Period 1 contains only hydrogen and helium. Here's period 2 consisting of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And here's period 3, sodium through to argon. The columns in the periodic table are called groups. These are the chemical families of elements with related properties. Here's group 1, which are called the alkali metals. Here's group 2, which is also called the alkaline earth metals. Then comes group 3, and so on. The block of elements in the middle of the table are called the transition elements, and can be thought of as a large chemical family. Using the group and period, we can identify exactly where an element is in the table. For example, magnesium is the element in period 3, group 2. The periodic table also divides up the elements which are metals from the elements which are non-metals. The non-metals are found on the right, and the metals on the left and the middle. There are many more metallic elements than non-metals. We can tell metals from non-metals because they have different chemical and physical properties, as we'll see in a later video. If you're not sure of the difference between physical properties and chemical properties, physical properties are those you can observe or measure, such as appearance, melting point, ability to conduct electricity, or hardness. Chemical properties tell us about how reactive a substance is and what it will react with.